Neumann trace inequality provides an upper bound on the magnitude of the trace of the product of two matrices A and B. A is of size m by n, B is of size n by m. A has a rank R, B has a rank S, and the upper bound makes use of the singular values of A and B. So matrix A, it has singular values, sigma A1 greater than or equal to sigma A2, all the way to sigma AR, which is strictly positive. So since the rank is R, then A has R strictly positive singular values. And so here they are in descending order. And matrix B, it has its singular value, sigma B1, sigma B2, all the way to sigma BS, because the rank is S. And the upper bound is sigma A1 times sigma B1 plus sigma A2 times sigma B2, and so on. You go all the way to the minimum of the two ranks. So to prove something like this, we start by writing down an exact expression for the trace of AB. And since we want to upper bound using the singular values, then it makes sense that we replace A and B by their singular value decompositions. And so this is exactly what we do here, is that we will replace A by its reduced singular value decomposition. And so this is a diagonal matrix, SA, of size R by R, and on its main diagonal, we have those guys, the strictly positive singular values of A. And for matrix B, we have the same story, but now this is a diagonal matrix of size S by S, and it has those singular values on its main diagonal. The columns of matrices UA, VA, UB, and VB are orthonormal. So basically, for example, if you focus on UA, if the L2 norm of each column is equal to 1, and if you pick two distinct columns, their inner product will be exactly equal to 0. Okay, so we'll use the reduced SVD to represent A and B. And then suppose that we have a matrix big X, which is of size P by Q, and big Y of size Q by P. Then we have this nice result that the trace of big X, big Y, so that's a square matrix of size P by P. This is equal to the trace of YX, which is a square matrix of size Q by Q. So basically, if you change the order, then the trace is invariant. The trace remains the same. So let's look here. We can think that we are multiplying two matrices. One of them is this guy, which is of size M by S. And then there is another matrix of size S by M. Okay, so AB is of size M by M, but now applying this rule for matrix trace, I can swap these two guys. So VB Hermitian will come here, and this matrix will come there, and now we have an S by S matrix. And the trace of AB is exactly equal to the trace of this S by S matrix. The matrices UA, UB, VA, VB can be expressed in terms of their columns. So basically here, A2, for example, is the second column in matrix UA, and here column VAR is a column vector that is the rth column in matrix VA, and so on. Now we will actually compute this trace. We will write a formula for this trace. So what about this product here, UASA? So this is UA1, the first column in UA, and then UA2, the second column, and so on. So this is matrix UA written explicitly in terms of its columns. And then SA is a diagonal matrix. So here we have sigma A1 and then followed by zeros. And then the second column will be 0, sigma A2, and then zeros, and so on. So when you do the product, so the product is a matrix of size big M times R. So we have in the product we will have R columns. So what will be the first column? The first column will be the first column in UA multiplied by this scalar here, which is sigma A. And the second column will be the second column of UA multiplied by sigma A2, and so on. Okay, so this will be UASA, and UBSB, which is the term here, will be obtained in a similar way. Now, the trace, by definition, is the sum of the elements on the main diagonal. So here we are interested in the trace of an S by S matrix. So what we will do is that we will write down an expression for element KK. So this is an element on the main diagonal of this S by S matrix, and then we will sum over index K from 1 to S, and so this will give us the trace. So what is element KK in this matrix here? So to obtain element KK, we will need basically the kth row in this matrix VB Hermitian, and then we will need those middle guys. Okay, so we will need UA, SA, VA Hermitian, and then from UB, SB, we will need the column K. Right, so if we take the kth row in matrix VB Hermitian, multiplied by this matrix here, UA, SA, VA Hermitian, and then multiply this by the kth column in UBSB, then this will be element KK. And to obtain the trace, we will later sum K from 1 to S. So if matrix VB, it has those columns, so if you take its Hermitian, then the first, what do? You take the first column, you transpose it, you convert it into a row, and then you take the complex conjugate. So basically, the first row in VB Hermitian will be VB1 Hermitian. Okay, and the second row will be VB2 Hermitian, and so on. So basically, the kth row in VB Hermitian is the kth column in matrix B, and then you take its Hermitian. Okay. So it will be VBK Hermitian. So this is the kth column in matrix, VB, and then you take its Hermitian. So it is converted into a row. It is transposed, and then you take the complex conjugate. And then we have UASA, then this is basically this matrix, and then VA Hermitian, so that's matrix VA, and then you take its Hermitian, and so you transpose the columns, you convert them into rows, and then you take the complex conjugate, and so basically the rows of VA Hermitian are basically the columns of VA after taking basically Hermitian, after transposition and the complex conjugation. And then we will take the kth column in this matrix. So UBSP is this matrix. So the kth column will be UBK sigma BK. So it is the kth column in matrix UB multiplied by this scalar quantity sigma BK. Now, if you have a row vector, this is a row vector times a matrix. So a row vector multiplied by the matrix from the left. So this means that I will take the row vector and I will multiply it by each column in the matrix. Okay, so the product of the row vector times the matrix is a row vector. And so the first element in the row vector is you take this row vector and you multiply it by the first column. The second element in the row vector, you take this row vector multiplied by the second column, and so forth. So basically we get a matrix that looks like this. Now we have this matrix, and it is expressed in terms of its rows, and it's multiplied from the right by a column vector. And so we can express this matrix column vector product as taking the first row and then multiplying it by this column vector. So this will be the topmost output in the resulting column vector, and so on. Okay, so the result of this matrix vector product will be a column vector. Its first element will be that you take this first row in the matrix times this column vector. The second element in the resulting column vector will be the second row here multiplied by this column vector, and so on. So now we were able to take element KK in this S by S matrix, and now it is expressed as a row vector times a column vector. And now finally we do the product, and the product is simply that we'll take this element by this element plus this element by this element and so on. And so the result that will give us element kk in our matrix of interest is a summation, and this summation has r terms because this row vector has r elements and this column vector has r elements. So it is a summation with index small l going from 1 to r, and then we multiply the lth element from this row vector by the lth element in this column vector. Okay, and so this will give us this quantity here. Now, are we done? No. To obtain the trace is basically a sum of the main diagonal elements of our S by S matrix. And so we need to take this guy here and we do a summation with K going from 1 to S. So this is basically the story so far. We took the trace of AB. So we took AB. Now we are interested in upper bounding the magnitude of the trace of the product by a sum that involves the singular values of A and B. So it makes sense that we start solving this problem by taking A and B and replacing them by their singular value decomposition. Specifically, we used the reduced SVD for matrix A and the reduced SVD for matrix B. We discovered that we can write down the trace of AB as the trace of this S by S matrix. And the S by S matrix contains basically those matrices that come from doing the reduced SVD of A and B. Then this is an S by S matrix. We focused on element KK in this matrix. So it's the kth element on the main diagonal of this S by S matrix. So we wrote down this element KK as a summation here. And then to find the trace, we summed over K. So that's an exact expression for the trace of AB. And it involves basically the singular values and the singular vectors of matrices A and B. Now, this is an exact expression. Now we will start doing upper bounding. And the first step is that we will apply the triangle inequality. We are upper bounding the magnitude of the trace. And so the magnitude of the trace is equal to the magnitude of the sum. And so by the triangle inequality, the magnitude of the sum is less than or equal to the sum of magnitudes. And so our quantity of interest is upper bounded by the sum, and then you apply the magnitude to basically the summand here. Just note that, this is a scalar. And this is also scalar. These guys are the strictly positive singular values of matrices A and B respectively. And so those are real valued positive quantities. And so, basically their magnitude, the magnitude of, for example, sigma AL is just itself, and the same for sigma BK. And so when the magnitude is applied, it's applied to this inner product, and it's applied also to this inner product here. Okay, so that's the first step. Second step is that we will upper bound this product of magnitudes by 1/2 of this guy squared plus 1/2 of this guy squared. And this follows simply from the following fact. If you have two complex valued quantities, alpha and beta, then of course the magnitudes are real valued and non-negative. So magnitude of alpha minus the magnitude of beta is a real valued quantity. And if we square that real valued quantity, then we definitely get something that is non-negative. Just expand this square, and so you will get magnitude alpha squared plus magnitude beta squared minus 2 magnitude alpha magnitude beta, which can be moved to the other side. Divide both sides by 2, and then you get this inequality, which will be applied to this product of magnitudes here. And now upper bound on the magnitude of the trace of the product AB can be written as two terms, two double sums. Okay. Now let's investigate those guys here. We wish actually that those guys sort of disappear because we want the upper bound on the magnitude of trace AB to depend only on the singular values. We don't want like the singular vectors to appear in the picture. Okay. So if we investigate this quantity or that quantity, we'll discover that if you sum any of these two quantities over K, or if you sum over L, then you get a sum that is upper bounded by unity. Okay, so this is what I mean, that actually we have four inequalities. If I take this quantity here, which is indexed by K and L, suppose that you sum over K from 1 to S, S is the rank of matrix B, then you get something that is upper bounded by 1. Suppose that rather than summing over K, you sum over L from 1 to R, and R is the rank of A. You also get a sum that is upper bounded by 1. Now, if you take this quantity, if you sum it over L from 1 to R, you get something that is upper bounded by 1. And if you sum over K, also you get something that is upper bounded by 1. Okay, so to see this, let's just focus on this guy and focus on the case that we do a summation over index small k from 1 to S, and the other three cases can be handled similarly. So suppose that you take this quantity here, so that's the magnitude squared of basically this inner product. Okay, so we have an inner product, the column vector VBK and the column vector UAL, and we are taking the inner product by taking the Hermitian of this vector into UAL and then taking the magnitude squared. What if we sum K from 1 to S? So the trick here is that we are summing quantities that are real valued and non-negative. So we definitely increase the value of the sum if we incorporate more terms that are real valued and non-negative. So we upper bound by the same summation, but we extend the summation index. Rather than stopping at S, we will go all the way to big M. Recall that matrix B is an n by m matrix, and S is its rank, which is less than or equal to the minimum of the two sizes n and m. Okay, so if we do this extension and go all the way to big M, so what are the vectors VBK now? So we started by doing the reduced SVD of matrix B. So B is UB SB VB Hermitian, and now VB was a matrix of size M by S, and basically its columns VB1 all the way to VBS. So now what are the new guys here? What is VB of S plus 1, VB of S plus 2, and so on? So those are vectors taken from the full SVD of matrix B, because matrix B also can be written as a unitary matrix UB bar, and this is an n by n matrix. It's unitary, so its inverse is its Hermitian. So UB bar times UB bar Hermitian is the same as UB bar Hermitian times UB bar, and both products are equal to identity of size n by n. Then we have a sigma B matrix, which is a matrix here in the left topmost part of the matrix. We have SB living, and then we fill the matrix by zeros. And then we have VB bar Hermitian, which is of interest to us here. And so VB bar itself is an M by N matrix that is unitary. What is this matrix? The first S columns in this matrix are simply the columns that constitute VB, which is used in the reduced SVD, the reduced singular value decomposition of matrix B. But now this matrix, it has those vectors, and in addition, it has those other vectors, all the way to VBM. Okay, and every vector in the matrix VB bar, every vector has a unity L2 norm, and the vectors are, or if you take two distinct vectors, they are orthogonal to one another. Okay, so that's the meaning that the matrix is unitary. Okay, so basically those are the vectors here. So we are making use now of the full SVD of matrix B. Now this is a complex quantity. This is a complex quantity squared. Okay, so Q is in C, then what is the magnitude squared of the complex number Q? So it is Q Hermitian Q, or it is Q conjugate Q. So basically, if you have a complex scalar, so the magnitude squared is the complex conjugate times Q. And if you have a matrix that is 1 by 1, then its Hermitian is just its complex conjugate. Okay, so what I will do here is that we want the magnitude squared of this complex quantity, then write down the complex quantity and write down here its complex conjugate. And its complex conjugate is simply its Hermitian. And so this will be UAL Hermitian times UBK Hermitian. So it's, VBK Hermitian, which is VBK. Okay. And so this is just a rewriting of the magnitude squared. Now note that we can take this UAL Hermitian outside and to the left, and this guy to the right, because the summation index is K, and those guys, they do not depend on K. So we have this summation here. What is this summation here? This summation is a sum of the outer products of the columns of matrix VB bar, which is the V matrix for of the full SVD of matrix B, right? So this sum of the outer products is simply VB bar times VB bar Hermitian, right? VB bar is VB1, VB2, all the way to VBM. And if you multiply by the Hermitian, so what is the Hermitian of this matrix? So the first row will be the Hermitian of this column, VB1 Hermitian, VB2 Hermitian, all the way to VBM Hermitian. And now if you do the multiplication VB bar Hermitian, you will get VB1 Hermitian. That's the outer product of vector VB1 with itself. Okay, and the sum okay, will, the sum, which is VB bar Hermitian, is the sum that we have here. Now matrix VB bar is a unitary matrix, so this product here is identity, because for a unitary matrix the inverse of the matrix is its Hermitian. So this product here is identity of size m by m, and so the product here is just UAL Hermitian UAL, which is the L2 norm squared of this column vector UAL, and that's the Lth vector in matrix UA. And as I said at the beginning, that the columns of this matrix are normalized so that they have unity L2 norms. And so this thing here is equal to 1. This thing here is equal to 1, which means that this summation that we started with is less than or equal to 1. And the same trick of using the, extending the sum and using the full SVD can be used to show that, those terms, again, they have this nice property that if you take those terms, this or that, and you do a sum over K or a sum over L, you always get a sum that is upper bounded by unity. So now we are very close to our desired result. Is this thing less than or equal to summation D from 1 to the minimum of R and S? So these are, R is the rank of A, S is the rank of B, and then we have sigma AD, sigma BD. Okay, now if we can show that this double sum here is upper bounded by summation D from 1 to the minimum of R and S, sigma AR, sigma AD, sigma BD, and if we can show that this double sum is upper bounded by the same quantity, D from 1 to the minimum of R and S, sigma AD, sigma BD, then basically the upper bound on the magnitude of the trace will be 1/2 this summation here plus 1/2 this summation here. So it will be upper bounded by the summation that is in the theorem. Okay, so this is basically the desired upper bound, that if we have two matrices A and B, then the trace of the product in magnitude can be upper bounded by sigma A1, sigma B1 plus sigma A2, sigma B2, and so on, till we reach the minimum of the two ranks. So can we take this summation or this summation and do this upper bounding? Okay, so now our problem is this problem here. Can we prove this inequality, that this single sum is superior to this double sum, summation k from 1 to s, summation l from 1 to r, sigma a l, sigma bk, gamma lk. So gamma lk is playing the role of this or of that. It won't matter. So gamma lk, the gammas are non-negative and they satisfy this property we talked about, which is that if you sum over L, you get a sum less than or equal to 1. If you sum over K, you get a sum that is less than or equal to 1. Can we show that this double sum is less than or equal to this single sum? And if so, then we are done. So here is the trick. These are the singular values of A in descending order. And what we can do is that we can take the smallest guy, sigma AR, so that's the smallest strictly positive singular value of A, and we can just call it eta R, where eta R is strictly positive. Okay, not a problem. What about sigma AR minus 1? So that's the singular value, that is greater than or equal to this guy. Rather than leaving it as is, I will write it as eta R, which is sigma ER plus a non-negative quantity. To take into account that this singular value is greater than or equal to that singular value, I will write it as eta R plus a non-negative quantity. Let's call it eta R minus 1. So what about this singular value, which is greater than or equal to sigma A R minus 1? I will write it as sigma eta R plus eta R minus 1. So these two guys are exactly equal to sigma AR minus 1. But, this one is superior to this one. So we will add here a non-negative eta R minus 2. And so on and so forth. So that this guy here will be eta 1 plus eta 2 all the way to eta R. Okay, so the idea is we will basically use R non-negative quantities, eta 1, eta 2 till eta R, such that sigma AR is eta R, sigma AR minus 1 is eta R plus eta R minus 1, sigma AR minus 2 is eta R plus eta R minus 1 plus eta R minus 2. Generally, sigma AL will be the sum of those etas starting from L all the way to R. So let's verify here that sigma AR, so if L is equal to R, then the summation here will have one term only, and the index of summation J will be equal to R, and sigma AR is eta R as here. Now, if L is R, if L is R minus 1, then this summation will go from R minus 1 to R, and we have two terms, and so on. So this is a way for representing the singular values, exploiting the fact that they are ordered like this. We can apply the exact same trick to the singular values of matrix B. So I will write down sigma bk as a summation I from k to s epsilon I. Okay, and so the idea is that this guy will be set equal to epsilon s, which is strictly positive. Now this guy, sigma bs minus 1, is greater than or equal to sigma bs, so I will write it down as epsilon s plus epsilon s minus 1, and so on. Okay, so these will be representations for the singular values that will be used later. Before doing that, this inequality will be proved by moving this to the other side and showing that this single sum minus this double sum is non-negative. Okay, so we'll take the single sum minus the double sum. We will combine them. So we will combine them by converting this single sum into a double sum. So I will take k from 1 to s, l from 1 to r, and then I will write sigma al, sigma bk. And then to obtain this single sum, I will use indicator l equals k. So this is 1 if L is equal to K, 0 if L is not equal to K. So if K is equal to L is equal to 1, then we will get the term sigma A1 plus sigma A1 times sigma B1. If L is equal to K is equal to 2, then we will get the term from here sigma A2 times sigma B2 and so on. So we will convert the single sum into this double sum, and to ensure equality, we will have to add this indicator, which tells you that these two indices, the indicator is 1 when these two indices are equal. And then we have minus the double sum. Then now combine these two sums, okay, from 1 to S, L from 1 to R, and then we have the singular values. And then we have indicator L is equal to K minus gamma L comma K, like this. Now write down the sigmas using the etas and epsilons, like this. So we have now, 4 sums, and they involve the etas, the epsilons, which are related to the singular values. And then we have this indicator L is equal to K, and then we have gamma LK again. Those are the non-negative quantities with this nice property. If you sum them over L, you get something less than or equal to 1. If you sum them over K, you get something less than or equal to 1. Okay, and then what we'll do is that we will change the order of sum. We have finite sums, so we can do the summation in any order of our choice. So for example, if we take K, so here we are summing K from 1 to S and then I from K to S. This is equivalent to summing I from 1 to S and K from 1 to I. Right? So so this is an illustration why this is true. So K, so the sum here, the outer sum is K. If you fix K, then you take I from K to S. So if K is 1, I goes from 1 to S. If K is 2, then I goes from 2 to S. If K is 3, then I goes from 3 to S, and so on. So alternatively, we can take I from 1 to S, and if we fix an I, then K will go from 1 to I. And we will do the same for the other two indices. So rather than having L from 1 to R and J from L to R, we will actually have J from 1 to R, and now L will be a summation from 1 to J. Okay, so we have basically a double sum. And those guys now do not, eta J, epsilon I, they do not depend on the indices K and L. So we can just put them separately here. And then we have a double sum with the indices K and L. We are done if we show that this quantity is non-negative, because eta J is non-negative, epsilon I is non-negative. And so if we show that this quantity here is non-negative, then basically we have that this difference will be non-negative and the double sum will be less than or equal to the single sum, and we are done. Okay, so that's the last step. Focusing now on this double sum here, what if you sum the indicator? So the indicator is 1 when L is equal to K and is 0 if L is not equal to K. So when K is 1 and L is 1, that's a term here that of 1. When K is 2 and L is 2, then we have another one, and so on. How many terms are equal to 1 in this double sum? So when L is equal to K is equal to 1, L is equal to K is equal to 2, all the way to the minimum of I and J. Okay, so this double sum here is exactly equal to the minimum of I and J, because we have a term of 1 only when the two indices are equal, 0 otherwise. So what about the double sum applied to those gammas? So summing K from 1 to I, summing L from 1 to J of gamma LK. What you can do is that, these are non-negative quantities. You can extend the summation over K rather than stopping at I. Remember that I basically goes from 1 to S. So we can actually extend this summation from rather than from 1 to I, 1 to S. And then we can exploit the inequalities we talked about earlier, that those gammas, if you sum them over any of the two indices, you get something that is upper bounded by 1. So summation k from 1 to S of gamma LK is less than or equal to 1. Summation gamma LK with L from 1 to R is also less than or equal to 1. So basically this thing is less than or equal to 1. And so we end up with a sum of ones, and this summation, it has j terms, so this is equal to j. And so the double sum is less than or equal to j. But I can redo this step. Rather than extending the summation with the index k, we can extend the summation with the index L. Rather than going from 1 to j, we can go 1 to r. Okay, so again, this is a sum of non-negative quantities. So by extending the summation, we have an upper bound. But what is the sum of gamma LK over L from 1 to R? So this is summation that has been proved to be less than or equal to 1. So we have upper bounding of this by 1, and then we are left with 1 plus 1 plus 1. How many times? The number of times, a number of terms in this summation, which is I. So this summation here can be upper bounded by G. So it is less than or equal to G. At the same time, it is less than or equal to I. So it is less than or equal to I and G. So that's it. So the double sum applied to the indicator will give the minimum of I and J. The double sum applied to gamma LK will give something that is minimum I and J or less. So when we take the difference here and apply the double sum, we will get a non-negative quantity. And then we multiply it by those guys that are non-negative. So the overall term will be non-negative, which means that this difference here is non-negative. And basically, this single sum is superior to this double sum. And this double sum itself is greater than or equal to the magnitude of trace AB. So the magnitude of the trace of the product AB is less than or equal to sigma A1, sigma B1 plus sigma A2, sigma B2, and so on.